Hi everyone. In this video, we're going to be looking at the two-way analysis of variance model, two-way ANOVA. So we're going to talk about the two-way ANOVA model itself and how we can use it to compare multiple groups and how we can assess and implement this model looking at a real data example. So we've already seen how to use one-way ANOVA, which is useful in the case in which we want to compare a single quantitative response variable across several groups from one categorical variable. Two-way ANOVA is sort of an extension of this method in which we still have a single quantitative response variable, but now we have two categorical variables that are determining many different groups together. So formally, the two-way ANOVA model is given by this. Yijk is equal to mu plus alpha I, where mu is the overall grand mean. Alpha I is the factor effect for the ith level or subgroup of factor A, plus beta j, where j is the jth level of factor B, plus an interaction term, and then finally plus a residual term, epsilon. So we'll learn how we can use this model to answer questions about a real-life data set later on in this activity here. An important consideration when fitting a two-way ANOVA model is that it does rely on some necessary assumptions to be true in order to conduct a valid inference. So valid f-tests and have valid confidence intervals. Those assumptions are pretty much the same as one-way ANOVA. They're all about the residuals, so we need normally distributed residuals. We need them to be homoscedastic, so we need equal variances across the groups. And as always, we need a random sample or have independent observations. Most commonly, this third assumption is most commonly violated by having repeated measures or time series data. So the two-way ANOVA model has a lot of different aspects to it, but we'll be covering it only very briefly in this activity. For a more detailed look at the two-way ANOVA model and different components of it, the Guide for Stat 216 document will be a great resource, as typed up a lot of formal equations and provided more detailed tables and additional information about the two-way ANOVA model that we just don't have time to cover in this activity. But for those who are curious, this information is here for your curiosity. Okay. So looking at a real data example on guinea pigs. So this was a study that was conducted during World War II, in that it was of interest to administer vitamin C to soldiers out in the field. This was important to do because the body produces a protein called collagen. In order to produce this protein, vitamin C is needed, and collagen is helpful in the process of healing wounds that we have, but also in maintaining heart health overall. So to this end, better methods for getting vitamin C to soldiers was being explored. So two supplement types or methods were considered: giving ascorbic acid, which was essentially a vitamin C supplement, like a pill, or traditional orange juice. So those are two different modalities or two different methods for giving the vitamin C. And then within that, we had three different dosage levels of each of those that were considered as well. Either a 0.5 milligram, 1 milligram, or 2 milligrams per day of either ascorbic acid or orange juice. And so to explore how this would affect vitamin C intake, a total of 60 guinea pigs were included in a study in what's called a balanced study design. So there were 6 total treatment groups, which each had 10 guinea pigs, yielding the 60 total guinea pigs. Since there was 10 in every group, and since it was an equal number in every group, that's why we call it a balanced study design. The 6 total groups comes from the different combinations of the dosage levels, of which there was 3, and the different supplement types, of which there was 2, yielding 6 total treatment groups. So a more detailed description of the study is available here if you're curious. Otherwise, that's all the information that we need to know that we can use a two-way ANOVA model in this case to explore the effect of the supplement type and the dosage level on the vitamin C intake of the guinea pigs. To measure the vitamin C intake of the guinea pigs, they weren't able to at the time directly measure vitamin C levels. So instead, as a surrogate or indirect measure, the researchers measured the odontoblast lengths in micrometers of the guinea pigs, a specific part of the tooth that is very much affected by vitamin C intake. The idea being if they were absorbing more vitamin C, these odontoblast lengths would be longer. So the odontoblast lengths in micrometers is the endpoint or response variable of interest in this study. Okay. Here's a table of 10 randomly selected rows from this data set, so 10 guinea pigs, although there were 60 guinea pigs in total, as a reminder. Okay. So we have the odontoblast length in micrometers, the supplement type being either ascorbic acid or orange juice for each guinea pig, and then the dosage level, the daily amount of the vitamin C type that they were administered. So to determine what the best way was to get vitamin C to the soldiers, be it some combination of orange juice and ascorbic acid or one of these dosage levels, the researchers used a two-way ANOVA model. And it may seem obvious that, well, the higher dosage level, of course, will give more vitamin C to be absorbed by the guinea pigs. But the idea was that this was costly, and during World War II, they didn't have all the resources in the world. So if a 0.5 milligram of vitamin C, a 0.5 milligram of orange juice did the job just the same as 2 milligrams of orange juice every day, then you go with the smaller dose because it's cheaper. Okay, so we use a two-way ANOVA to see how much can we get away with and what's the optimal treatment combination here if we want to maximize vitamin C intake. Right. So what are our response variables and explanatory variable in this case? I think I already mentioned this, but our response variable was the odontoblast lengths in micrometers. We had 2 explanatory variables. The supplement type, which was ascorbic acid or orange juice, and the dosage level, which was 0.5, 1 or 2.0 milligrams per day. So this is what makes it two-way ANOVA. We have two categorical variables and a single quantitative response variable. Okay. So what is n? So n is the overall sample size. In this case, although there's 10 observations or guinea pigs in each treatment group, there were n equals 60 total guinea pigs. Okay. What are A and B in this scenario? So we say that factor A is the supplement type and factor B is the dosage level. But notation-wise in two-way ANOVA, when people say capital A, they're referring to the number of subgroups or number of levels of factor A. In this case, that's 2. The subgroups being ascorbic acid and orange juice. For B, we have that B is equal to 3, which is the number of subgroups of factor B. Okay. With factor A being the supplement type and factor B being the dosage level. Okay. So now we have some SAS output at the bottom of the document that give us some side-by-side box plots. We'll zoom in a little bit here. We have some side-by-side box plots showing the ascorbic acid, odontoblast lengths, the orange juice, odontoblast lengths, and then also stratified by dosage level. So we have these box plots to show. We can see, without running the two-way ANOVA, that the higher the dosage length, the higher the dosage level, the longer the odontoblast lengths were typically. And for orange juice versus ascorbic acid, it looks like orange juice had maybe a higher or longer odontoblast lengths on average for the guinea pigs given orange juice as compared to ascorbic acid. We can see that's the case in the table, in the tables we get from proc means, from the means procedure. Orange juice had higher average, and then the higher the dosage, the higher the average odontoblast length. Okay. So let's see, which supplement type produced the greatest odontoblast length on average? So orange juice and let's see what that number was. So we go back down to the proc means table. Orange juice had a mean of 20.66. Okay. 20.66 micrometers. Which dosage level produced the greatest odontoblast length on average? So that was the 2 milligrams per day dosage yielded the greatest odontoblast length on average with 26.10 micrometers. Okay. So sometimes it's as simple as you take the highest subgroup of factor A and the highest subgroup of factor B, and then the combination of those two will give you the largest response variable on average. But when there's an interaction in the data, or sometimes just by chance, that's not always the case. It could be, for example, that maybe at really high dosages of orange juice, it actually becomes harmful for the guinea pigs, and so their teeth didn't grow as much. Like their body shuts down maybe and stops absorbing vitamin C. Well, while conversely, maybe with ascorbic acid, you can give it at really high doses and the vitamin C intake keeps going up. So if there's sort of differential effects depending on the combinations of the two factors, in this case, the dosage and the supplement type, we say there's an interaction between the factors. So in this case, looking at which combination gave the greatest odontoblast lengths, we may expect it to be the 2 milligram and orange juice combination, but if we look at the data, if we look down at this next table, which gives the all 6 treatment groups, all of the subgroups. So we have 0.5 milligram of ascorbic acid, 0.5 milligram of orange juice, 1 milligram of ascorbic acid, 1 milligram of orange juice, and so on. Which subgroup had the largest value? We expected it to be 2 milligrams of orange juice. It's actually 2 milligrams of ascorbic acid with 26.14 micrometers. Okay. So this doesn't guarantee that there's an interaction just based on these summary statistics, but certainly raises some suspicion that there may be an interaction going on between these two factors. And we can formally test for this in the two-way ANOVA modeling process. Okay, so the 2 milligrams per day of ascorbic acid yielded the greatest odontoblast lengths on average with 26.14 micrometers. And now we can provide the values of SS groups, SSE, and SS total, just like in one-way ANOVA. Okay, so I would recommend copying these blueprint interpretations from the guide for Stat 216 document. Okay, so if you go, starting from the top, there's a two-way ANOVA section. And then we have this ANOVA table, and we can copy these blueprint interpretations. All right. Saves us a little bit of typing. Okay, so SS groups, let's get the values of these first. SSE, SS groups, and SS total. So we'll get these from the ANOVA table. So if we scroll down to the SAS output, the ANOVA output that we're going to be interested in here is going to be in this section that has the title, the GLM procedure, which stands for Generalized Linear Model Procedure. The two-way ANOVA model is a specific case of a regression model, and more generally, it's a specific case of what's called a generalized linear model, which is a large class of regression type models. So here, SS groups is going to come from the model sum of squares cell. So right here. So SS groups is 2740.10. SSE 712.106. And SS total 3452.21. Maybe we'll round this one to 2 decimal places as well. Okay. So we get the numbers, and then we want to interpret them in context too. So this is the amount of variability in the response variable. So in the odontoblast lengths. Important to include units of measurement here too in the odontoblast lengths. Okay, so we'll update that for all of them in the odontoblast lengths. Odontoblast lengths. Explained by both of the independent variables. So instead of saying both of the independent variables, we'll say by the supplement type and the dosage level. Combination of the supplement type and the dosage level. And by updating the response and independent variables, we now have valid interpretations and values for all of the 3 SS's asked for here, the SS model or SS groups, sum of squared errors, and sum of squared total. So SS groups is representing how much variability in the response is explained by the 2 factors. SSE is describing how much variability is unexplained in the response by the 2 factors, supplement type and dosage here. And then SS total is the total amount of variability in the response variable. In this case, the odontoblast lengths in micrometers. Okay. This was similar to one-way ANOVA, with a little bit different interpretation for the SSE and SS groups. We also have now SSA and SSB. Okay. So we'll get those blueprint interpretations as well from the guide for Stat 216 document. And we'll update it just like before. So instead of response variable, we'll say the odontoblast lengths in micrometers. Explained by factor A, and instead of factor A, we'll say by the supplement type. And instead of factor B, we'll say by the dosage level. And then we still need to get these numbers as well. Okay, so SSA, we go down to the ANOVA table, we'll see this type 3 sum of squares, type 3 SS. This is where we want to get these values from. So factor A is supplement. So this gives us our SSA right here, 205.35. And then SSB is right here, since factor B was the dosage level. So 2426.43. All right. So those are new for a two-way ANOVA as compared to one-way ANOVA, but that's how we can interpret those values in context. A large, big first step in the two-way ANOVA modeling process is to first look at the overall F-test for the model. So in this case, for the guinea pigs example with the vitamin C, the null hypothesis for the overall F-test, the symbols get a little bit more complicated, so we'll give this one in words rather than using the Greek symbols. So we'll say our null hypothesis is that the supplement, type, and dosage, along with their interaction, don't explain a significant amount of variability in the odontoblast lengths. Whereas our alternative is that those two factors and their interaction do explain a significant amount of variability in the odontoblast lengths. Okay. You can see a general blueprint interpretation for this overall F-test for the two-way ANOVA model in the guide for Stat 216 document, but here we're just giving it right away for this context. So that's what we're testing. Before we can conduct the overall F-test, we need some conditions to be met, some assumptions to be true in order for this inference to be valid, in order for the p-value that we end up getting to be valid. Okay. So we looked at the assumptions before. We need that, and we can check the guide for Stat 216 document as well. Okay. We want to check assumptions. We need these three things. Okay. So we need normality. We must be able to assume that the residuals are normally distributed. Okay. So we can check the 3x3 grid of diagnostic plots that we'll get from SAS. This is how we'll check all of the assumptions for the two-way ANOVA model. For normality, we're looking again, just like one-way ANOVA, the same exact way. We're looking at the QQ plot and the histogram. So the histogram is fairly bell-shaped here. It's unimodal, decently symmetric. That supports normality. The QQ plot, most all of the points stay close to the diagonal line here, also supporting normality. Okay, so let's write that out. So okay, so normality seems good here. Let's check out homoscedasticity, the equivariances assumption. So we need that the vertical spread of the points on the residual by fitted value plot are fairly constant as we go from left to right. Okay, so let's check that out. Again, going back to our 3x3 grid of diagnostic plots, we look at the top left one for checking the homoscedasticity assumption. So in this residual by predicted value plot, we look at this vertical spread going left to right. It oscillates and changes somewhat, but there's not a clear or evident outward fanning pattern or funneling, nothing like that. There's nothing too problematic here. This seems to support the homoscedasticity assumption. Okay. We don't need to be too picky. Again, for examples of how this plot would look if assumptions were violated, I created some examples in the Guide for Stat 216 document, where you can go to the residual by predicted value plot section. Okay. And here, for example, in these four, the bottom right one, this is how it looks when homoscedasticity is met. Okay. And actually for C here, this is also homoscedastic residuals. Okay, a constant vertical spread from left to right. So they don't need to be perfect, but here's problems when it's outwardly fanning. In this case, it's funneling. That's where there's problems. So here's an okay plot. The residuals are homoscedastic and other examples. So you can always refer back to these examples if you're unsure about checking this assumption. Okay, so here, and we must assume that we have a random sample. Okay, so since these are all separate guinea pigs, we'll just assume we have a random sample. Ideally, these guinea pigs would have been randomly selected from the population of all guinea pigs. Not really feasible in real life, but you try your best. You know, it makes a difference how much this assumption is met, right? Like the fact that we don't have repeated measures is good. We can rely on our results more. Okay. There's special types of ANOVA models for repeated measures, but we won't cover those here. All right, so now looking at the result of the one-way of the overall F test for the two-way ANOVA model. Okay, let's get our F test statistic. So we get this from the ANOVA table here. Okay, so our F test statistic is the F value 41.56 here. E-value. E-value, we also get right next to that number. So that was less than 0.0001. Since the p-value is less than 0.05, we reject HO. Since the p-value is less than 0.05. Okay. So we say, and here we are following the guide for stat 216 document gives the steps for this process here. We're following the overall F-test directions here. Okay. Specifically, we're looking at, we're now into step 4. So this is a statistically significant result since we rejected HO. So we can copy this example blueprint interpretation here. We have sufficient evidence that alternative hypothesis in words. Okay, so let's look at what our alternative hypothesis was. Right here. We can copy that. Okay. So there's our interpretation of the result. It's somewhat vague and ambiguous. We're saying we have evidence that the supplement type and dosage level in their interaction do explain a significant amount of variability in the odontoblast lengths. We're not really saying which supplement type was best or which dosage level was best. All we're saying is that the odontoblast lengths did vary by treatment group, okay, on average. So after you conduct or implement an overall F-test for the two-way ANOVA model, for the full two-way ANOVA model, the next step you always do is to consider testing the interaction term. So what we're doing here is in this full model, we called it, we're modeling the odontoblast lengths Y using the effect of the supplement type, the dosage level, and their interaction. It may be the case that you can have a good model that does not need an interaction term. You can just have what we call the main effects of factor A and factor B. So we can use the data that we observed to decide if we need to account for an interaction or not between factors A and B by conducting an F-test of the interaction term. So how we can do that here is we first give our hypotheses. Oops. So a formal statement of the hypotheses is like this: HO and HA, which again, there's a section in the guide for stat 216 document that gives these blueprint hypotheses. And then we'll say where alpha, beta, IJ is the interaction between the ith supplement type. So I is indexing the supplement types, and the jth dosage level. J is indexing the dosage levels. Okay. So this is using some Greek symbols, right? To say in words essentially what we're testing that the effect of the dosage level on the odontoblast lengths does not vary by supplement type. We're seeing if that's true. If we have evidence that it does vary by supplement type, we're testing to see that. Okay. So one thing related to the interaction term, which is what we're focusing on here, is the SSAB term, sum of squares AB. So looking back at our table output down here, we have supplement times dose. Okay, not times 2, times the dosage. And the value here is 108.32. That's our SSAB. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Okay, and we have a blueprint interpretation for that value right here from the Guide for Stat 216 document. And just like before, oops, forgot to turn this one blue. Just like before, we'll update what the response variable and the factor names are for this context. So Donta-blast lengths in micrometers. Explained by the interaction between, and factor A is the supplement type, and factor B is the dosage level. So that's how we can interpret that value in context. This sort of quantifies how much the interaction between the two factors is causing the response variable to vary. But the units depend on the problem at hand. So this is, the units are squared micrometers, which makes it a little bit hard to understand or grasp. Like, is this a big number? Is the interaction describing a lot of the variability in the response or not? It depends on the context. It would depend on the units of measurement. So often it's easier or best practice to look at the a graphical display to explore if an interaction appears to be present or not. And we can do that by looking at what's called a means plot. A means plot. So if we scroll all the way down here, or SAS labels it an interaction plot. Their software calls this a means plot sometimes. So the points on here are the odontoblast lengths for a single guinea pig. So like one green circle is one guinea pig. And the lines are connecting the different treatment group means. Okay. So we have, for example, green is the 2 milligram groups. So this is connecting the, right here's the average odontoblast length for 2 milligrams of ascorbic acid, which is what all of these green guinea pigs got here. And then over here is all of these green guinea pigs are the ones who got 2 milligrams of orange juice. So right here where this line is their average odontoblast length. So in other words, very similar between these two, 2 milligrams of orange juice versus 2 milligrams of ascorbic acid. And we have similarly for the other groups. So this plot is important because if there is no interaction between factors A and B, then all line segments will be parallel on this plot. In other words, they'll all have the same slope. They'll all run parallel to each other. If the angles of the lines differ for any segments on the plot, that suggests there's an interaction present. And sometimes the lines even cross, although they don't have to for there to be an interaction present. It just needs to be that the slopes or angles of the lines are not the same. Okay. So in this case, the red and the blue line here are quite parallel. So that suggests there's not an interaction. But when you look at the green line, this slope is almost zero. It's flat, whereas these ones have positive slopes. So because these are different, they're not exactly parallel. Overall, this plot suggests there is an interaction present. So to emphasize that again, because not all lines are parallel, not all line segments are parallel in this plot, that suggests there is an interaction present between the supplement type and the dosage level. Okay. We can say that here. So since the lines were not all parallel, let's now conduct the F-test for the interaction term. If this F-test is statistically significant, that means the interaction is important and we should keep it in our model. If it's not statistically significant, that means we should drop the interaction term from our two-way ANOVA model and refit it with just the main effects of factors A and B. Okay. So let's consider if we should drop the interaction term or not. So we look at the F test statistic value here, which is 4.11. And we also have the p-value, which was 0.0219. Okay, so since the p-value is less than 0.05, we reject HO. Okay, so interpreting our result, let's look at the, again, Guide for Stat 216 document. There's a subsection about testing an interaction between factors A and B. Let's look at the interpretation, step 4 here. Okay, so this is a statistically significant result, so we'll copy this one. Right. And to get our alternative hypothesis in words, let's scroll back up to where we gave that. So our null hypothesis was that this was true. Okay, so our alternative hypothesis is the opposite of that. So it's that it does. So here's our conclusion for the test of the interaction term. So in other words, the interaction was important and we should keep it in our model. So with a two-way ANOVA model, you'll notice you also get these F test statistics for the main effects of factor A, supplement, and factor B, dosage. Anytime you have an interaction term in a model, you must keep the components of that interaction in the model as well. For sensibility reasons and also accuracy of the model. It won't make sense anymore if we dropped, for example, supplement, but kept the interaction of dosage and supplement in. There's a number of reasons, both like theoretically and practically, why that does not make sense and it's bad to do. So anytime you have an interaction, you keep all of the subcomponents. If we had dropped the interaction term from the model, we could then consider dropping dosage or supplement from the model as well. But again, since we're keeping the interaction term, which is what we look at first always, we just keep the whole model now as it is, because we must keep the subcomponents of the interaction. So now that we have our final model, it's statistically significant, the interaction is important, we proceed to a post hoc analysis. So for the post hoc, we're going to figure out which treatment combination exactly do we expect to give the greatest odontoblast lengths on average. Okay. So we get a lot of information from the post hoc. There are, if we scroll all the way down here, there are essentially 6 different treatment groups. So every combination of supplement type and dosage. Here's the average odontoblast lengths for each of them. And then here, just like the post hoc for one-way ANOVA, is a matrix or table of p-values for 2 sample t-tests comparing all pairwise combinations of the 6 different groups. Okay. And this matrix is what we call symmetric, in that the bottom triangular portion of the matrix is exactly the same as the upper triangular portion of the matrix. So we actually only need the bottom triangle half to see all results of the different comparisons. So for example, in the first cell here, this is the p-value for a 2 sample t-test comparing groups 1 and group 2. So comparing ascorbic acid 0.5 milligram to ascorbic acid 1 milligram. Okay, so they were different. The p-value is small. And we can see their means were quite a bit different too. Okay. Some groups that did not differ, so groups 3 and 4, or 3 and 6, I should say, had a p-value of, when rounded to 4 decimal places, was 1. It wasn't exactly 1, that's just SAS rounding. The p-value won't be exactly 1 unless the sample means for groups 3 and 6 were exactly equal, which they're not. But they're very similar, 26.14 and 26.06. So those groups were not, their difference between those groups was not statistically significant. Let's go back to what we were wanting. Okay, so we want a interpretation for the confidence interval for the difference in the average odontoblasts between 0.5 milligram and 1 milligram of ascorbic acid. Okay, so let's get the bounds for our confidence interval first. Okay, so 0.5 milligram and 1 milligram of ascorbic acid. SAS gives you confidence intervals for all those pairwise comparisons. Okay, so 0.5 and 1, that's groups 1 and 2. So 1 and 2. Our confidence limits are here. I think that was right. Hard to remember by the time you scroll up. Okay. Yep. Okay. So we can convert these to positive numbers, but we have to be careful about which group was higher when we do that. So anytime we interpret the bounds for a confidence interval, we want to only use positive numbers. So we have to change them to be positive, and then for the interpretation, keep in mind which of the 2 groups was higher in our wording of the interpretation. Okay. So we are I guess it was milligrams per day. Okay. So we are 95% confident that the mean odontoblast lengths for 1 milligram of ascorbic acid is between this and this micrometers, lower or greater. So we know the confidence interval was negative. And SAS does the order of subtraction being group 1 minus group 2. So since it was negative, the difference between them was negative. That means that group 2 was bigger than group 1. So SAS does group 1 minus group 2. If that was negative, that means group 2 was bigger. That's one way to check. Maybe an easier way is you can look at the sample means for each group and see which one was bigger. So here, 1 milligram of ascorbic acid, the sample mean was bigger than for half a milligram. So group 2 was bigger. That will always align with how your confidence interval should be interpreted as well. So for 1 milligram, which was group 2, that was greater than half a milligram. Okay. And so we can interpret all the other confidence intervals. They give you a total of, there's 6 choose 2 comparisons, which is 15. It's a lot of comparisons, but we'll just do that one. And we can also lastly decide, okay, well, in this study, what was the best treatment combination to get the greatest odontoblast length on average? So to achieve the so let's look at the p-values. Okay, we have groups 1 through 6. Often helpful to start by looking at, okay, which group had just the biggest sample mean? And were they bigger than other groups based on the p-values? So group 3 was the biggest in terms of just the sample means. But is 0.08 bigger than group 6? Is that really meaningful? That's where the p-values can help us decide that. Like, is that difference in size meaningful or not? Okay. So looking at group 3 and all of its associated p-values, okay, it had very small p-values indicating, since it was the largest, that it was bigger than all of the groups except groups 5 and 6. If you look at the p-values for that, we had 0.2936 and nearly 1 when rounded. Okay. So that tells us, since group 3 is 2 milligrams of ascorbic acid, that to get the highest odontoblast lengths on average, one could use ascorbic acid 2 milligrams, orange juice 1 milligram, or orange juice 2 milligrams. Okay. And let's make sure that those were different than the other groups as well. So 2 milligrams of ascorbic acid was higher, but what about these other two groups that we mentioned? The orange juice ones. Okay, those are groups 5 and 6. Okay, so if we look at the table in groups 5 and 6, they had small p-values when comparing to everything else except groups 3 for 5, group 3 and group 6, which was ascorbic acid 2 milligrams and orange juice 2 milligrams. And then for group 6, it was all of them were really small except compared to group 3, ascorbic acid 2 milligrams, and group 5, orange juice 1 milligram. So they all, depending on which group you were looking at, which treatment group, it tells us a consistent story. There was 3 groups that were better than the others. And we can see that's the case too, looking at the sample means. Okay. 26.14 micrometers for ascorbic acid 2 milligrams, okay, and 26 and 23 about for the orange juice high doses. So if the military had all the money in the world, and it didn't matter, like they could do any supplement type, any dosage level, we'd say go for the ascorbic acid, 2 milligrams. That was the highest. But if there's cost constraints and maybe orange juice is cheaper, we could say use 1 milligram of orange juice because that was tied for the highest in terms of as far as the p-values are concerned. Used the least amount of orange juice and it's cheaper than ascorbic acid. So you could recommend going with this treatment. Okay, so at this point, we would say any of these 3 groups are fine that we mentioned. It would depend on how much they cost the military to produce or use those. Okay. So that's it for two-way ANOVA. That's the last part that we'll look at here. And that concludes this activity. Thanks.